Hey, in this video, we are going to check out congruence transformations. So first of all, we're going to learn, the first thing to look at this is what is congruence? What is that weird word? And then the second thing is how to identify a congruence. We're going to teach you some tricks on that. So let's check it out. What in the world is congruence? You may be asking. Well, that is simply when two figures have the same side lengths and angles. So look at this example down here. We have triangle ABC and we got triangle DEF. Now, what do you notice about these two? Well, basically, all the angles of ABC, 60, 90, and 30, is the same or congruent to DEF, which is 60, 90, and 30. And then check out the side lengths as well. So what do we notice about that? Yeah, all the side lengths are the same as well. 10, 5, and look at the last one, 8.6. Okay, so bam, these are definitely congruent. All the sides and angles are the same. That's it. If you understand that, you got the concept of this whole section. It's not too bad, right? Now let's look at an example. You may be asking, well, what's a situation where it's not congruent? All right, well, look at this. This one, X, Y, and Z, triangle X, Y, Z, the angle is 65. This angle is 60. Bam, these are not congruent. Okay, so you can't say that those two triangles are congruent. How you would demonstrate this or write this down mathematically is you have triangles ABC and triangles DEF. Here's what you would write. You would write that angle A is equals or congruent to angle D. So look at that syntax. Look at that the symbology. Look at that angle sign. Awesome, right? So that's how you do the angles. And side lengths, you just do segment AB with the little line over top is congruent to DE. So what's that saying is that AB, look over here, that side length is 5, is equal to DE, which is also 5. So the order of your letters matter. You can't say BA is congruent to DE. That would be kind of incorrect. Don't be saying that stuff, okay? So pay attention to the order of the named points, the named vertices, and make sure that you kind of keep that straight. They're not always going to be like perfectly next to each other like that. You know, this one might be rotated or whatever, and they could still be congruent, okay? So the last concept, check this out. How in the world would you know if two figures are even congruent? So here's one way how you would demonstrate that. So if you can use rigid transformations, think about what in the world is a rigid transformation? Well, from the previous sections, you know that it is the reflections, it's rotations, and it's translations. Okay, so those three are rigid transformations. And if you can use those three rigid transformations to map one figure onto another, then they are congruent. All right, so that was like a lot of crazy math talk, but like, let's break it down. So say you got triangles ABC and triangles EFD, okay? So maybe they have a attraction for each other. They're like on a dating site and they're wondering if maybe they have some congruency. All right, so let's check it out. Let's see if they're compatible. Let's see if they're congruent. So the first step that I would do here, I would notice that like, hey, look at vertex B and look at vertex E. I think I can get those 2 points together. So that would be a translation of 1, 2, 3, 1, 2, 3. Okay, so a translation, right, big T, of 3, -3, of triangle ABC will get me over here, okay? So we're going to go from this graph to this graph here. Bam, all like B and E are kissing now. That's good, right? So this side is all lined up. So this would go 1, 2, 3, 1, 2, 3, and that point would be there and there, okay? The next step, we don't know if they're congruent yet. They got some chemistry, but we don't know if they're congruent. Okay, so it looks like what would you do in this situation? Okay, so we got ABC and EFD. It looks like if we bust down a reflection over this line of symmetry right here, these two triangles are going to pop right on top of each other like that, right? So bam, two what do you call them? Rigid transformations will map these two figures on top of each other, so we know that they're congruent. So a combination of the translation and a reflection over the line y equals x shows us that these two triangles are congruent. So if I was writing the answer for that, it would be some type of combination of this statement right here. All right, I'll stop being lazy. If you really want to write it out, I would write the reflection of y equals x, and this is from the last section, that compound isometry, right? Of a translation of 3, -3, of triangle ABC will equal triangle EFD. Okay? Now here's the big secret that they're kind of trying to hide from you and keep from you. Any rigid transformations will, here, let me write, will always be congruent. Okay, so if I was doing like, oh, let's rotate about point M, triangles ABC, to make triangles EFD, and the question was asking, are these two triangles congruent? The answer is yes. Okay, because it's just a rigid transformation. No angles are changing and no side lanes are changing. So I am comfortable in this situation saying that, yeah, angle A is congruent to angle E, angle B is congruent to angle F, and you know the next one. And the same thing, how would you do the side lanes, right? So I know that side lanes AB is congruent to EF. Okay, I'm not going to bore you and write down every single side lanes, but you get the idea. So if it's any type of rigid transformation, yes, it will always be congruent, because we know that in rigid transformations, side lanes and angles are preserved, all right? So that is this section. If you have any questions, make sure to ask your teacher, and I'll see you guys in the next section.